Have you ever noticed how AI seems to uh, pop up everywhere in your daily life?
Oh, definitely.
From just asking your smart speaker for the weather to, that surprisingly human-like chat support you sometimes get online.
Right.
It feels like these artificial intelligences are doing more and more complex things. But have you ever stopped to wonder what's truly going on, like behind the scenes?
Yeah, what makes them tick?
Exactly. What makes one AI so different from another?
It's a great question because what feels like a smooth interaction often hides, well, vastly different internal workings, different levels of sophistication.
Right. So in this deep dive, we're going to unpack the very foundations of artificial intelligence. We'll explore the evolution of AI agent architectures.
Think of it like climbing a ladder of complexity.
Yeah, exactly. Breaking down the different capabilities of these agents from the really basic ones all the way up to the most advanced.
And our mission today is, well, to give you a shortcut, a way to understand the key nuggets about how AI actually thinks.
Or maybe doesn't think in the way we imagine.
Or perhaps more accurately, yeah, how it processes information and makes decisions. And understanding this can really illuminate the AI tools you use every day.
Helping you grasp the core differences and maybe some surprising nuances that define AI's intelligence.
Precisely.
Okay, let's unpack this.
Yeah.
Starting at the very bottom of that ladder. Simple agents.
Foundation.
Imagine these as the absolute simplest form of AI. Their core concept is just a direct stimulus response. Input leads to output.
Right. You give them an input, they give you a predefined output. That's it. No internal map, no memory of what happened before, just straightforward mapping.
Almost robotic, really.
Yeah, in a sense. But what's often missed about them is their surprising efficiency.
Efficiency? How so, if they're so simple?
Well, because they don't have complex internal states to manage, they excel in environments that are static, deterministic, completely predictable.
Okay.
Like Wooldridge and Jennings pointed this out way back in '95. They're perfect for basic tasks. Think automatic document retrieval or controlling sensors and actuators on a production line. Oh.
Okay, so very specific, very controlled situations.
Very niche, very specific, but very good at that particular job.
But of course, that simplicity comes with a massive trade-off, right?
Absolutely.
The big lesson here isn't just their limits, but how their complete failure when things change highlights a kind of fundamental fragility.
Fragility. Tell me more.
Well, it shows that even more advanced AI relies on underlying assumptions about the world. And if those assumptions break...
The whole system can struggle. Yeah.
Right. With simple agents, if there's any deviation from their programmed rules, you get system fragility, often leading straight to operational failure. Their usefulness is really limited to those narrow, static worlds.
Which raises a key question. If they're so rigid, why even use them?
Good point.
What's striking, though, is that despite the rigidity, they're predictable behavior. The fact that it's easy to verify exactly what they'll do, that offers real advantages.
In safety-critical applications.
Exactly. Think about situations where transparency and predictability are absolutely paramount.
Like controlling medical equipment or maybe part of the power grid.
Precisely. Even if it means limited autonomy, knowing exactly what the agent will do under specific conditions can be a huge benefit for reliability, especially when lives or critical infrastructure are involved.
Okay, that makes sense. Precision is key there. But what happens when the world isn't so predictable? Which is, let's face it, most of the time.
Right. Then you need something more. That's where we need a different kind of intelligence. Enter reactive agents.
Built for real-time adaptation.
Yeah, these are a step up. They incorporate real-time environmental adaptation, but crucially, without complex internal maps or explicit planning.
So how do they adapt them?
They rely on their immediate perceptual states. What they see, hear, or sense right now dictates their actions.
Like a sophisticated reflex.
That's a good way to put it. This real-time adaptability allows them to operate effectively in dynamic, partially observable environments, places where things change and you don't have all the information.
Like robotics.
Yep. Robotic exploration is a classic example.
Yeah.
Or multi-agent navigation scenarios where lots of agents have to coordinate without a central plan. They're constantly reacting to what they perceive right now. A very sophisticated instinct machine, as you said.
Is there a memorable example of this?
Oh, definitely. Think about Steele's simulations of reactive agents in a Mars Explorer system.
Mars Explorers. Cool.
Yeah, they use something called subsumption architectures.
Subsumption. What's that?
Think of it as a layered control system.
Wow.
Simpler, immediate behaviors like avoid obstacle can take over or subsume More complex ones like go towards target if needed.
Ah, so the urgent stuff overrides the plan.
Exactly. It makes the system incredibly robust and reactive without needing a grand internal plan. And they achieved near-optimal performance in tasks like collecting resources and avoiding obstacles, even under really tough, unpredictable Martian conditions.
Wow, so simple rules lead to smart results.
Right. It highlights the strength of modular hierarchical designs, especially in systems like, say, swarm robotics.
Where you have lots of simple robots working together.
Precisely. Decentralized local rules can lead to powerful collective problem solving. What's truly insightful about reactive agents is how seemingly intelligent, complex behaviors like navigating Mars can emerge from purely local, immediate reactions.
It proves you don't always need a deep thought process to solve complex physical problems.
It's emergent intelligence. Pure and simple, in a way. However, there's a catch.
Ah, the limitations.
Their limitation is their inability to reason about past experiences or anticipate future consequences. They're still very much stuck in the present moment.
Which restricts their use if you need strategy, right?
Exactly. Domains requiring strategic planning or long-term goals, reactive agents aren't the best fit.
Okay, so if reactive agents are stuck reacting, how do we get AI that can actually plan? Look ahead.
That's the next step up the ladder. Deliberative agents.
Deliberative. Sounds like thinking.
It is, in a way. They directly address the limitations of reactive agents by using internal symbolic models and explicit reasoning mechanisms.
Symbolic models, like maps or lists.
Sort of. They build an internal representation of the world and their goals. This lets them plan and execute long-term, goal-oriented behavior. It's almost like they have an internal mental whiteboard where they explicitly map out steps before acting.
Instead of just reacting on instinct.
Right. And a key framework often used here is the belief, desire, intention framework, BDI for short.
Belief, desire, intention. Okay, break that down.
Sure. It structures the agent's knowledge. Beliefs are its understanding of the environment, what it knows. Desires are its goals, what it wants. And intentions are its chosen plans for action, what it commits to doing.
That sounds much more structured. And maybe easier to understand why it does what it does.
That's a key benefit. It makes the decision-making process more structured and, importantly, often more explainable than just a pure reaction.
This sounds like something we'd need for really complex, maybe high-stakes applications.
Absolutely. Deliberative agents are particularly well-suited for complex domains needing high levels of responsibility and adaptability.
Like what?
Think air traffic management coordinating multiple planes is critical. Or maybe patient care management in a hospital.
Okay, yeah. Definitely need planning there.
And research, like work by Nick Jennings back in '93, showed they could coordinate plans and adapt to evolving constraints in distributed systems. Things like power grid management. They achieved superior results compared to simpler approaches.
That sounds incredibly powerful, but I sense a but coming. There must be a trade-off.
There always is.
All that planning and reasoning has to take a toll, computationally speaking.
It definitely does. The deliberative approach introduces significant computational overhead.
Meaning it's slow or needs a lot of processing power.
Both, potentially. Especially in volatile environments where a plan might need to be reevaluated constantly. Imagine trying to make a detailed plan when everything around you is changing every second.
Yeah, the plan would be useless almost immediately.
Exactly. And some interesting research by Kinney and Georgiev highlighted these trade-offs. They categorized agents as bold, normal, or cautious, based on how frequently they stopped to reconsider their plans. Cautious agents replanned all the time. Bold ones stuck with their plans more.
And what did they find? The cautious ones did better.
Surprisingly, no, not always. What they found was fascinating. In high-pressure environments, the bold agents, the ones that didn't overthink constantly, actually outperformed the cautious ones.
Wait, really? The ones that thought less sometimes won?
In those specific conditions, yes. It underscores the importance of tuning the agent to the domain. You need the right balance between deliberation and just getting on with it. Sometimes overthinking is detrimental.
Wow, that's a surprising nugget. It suggests we need to be really smart about how much an AI plans, depending on the situation. Okay, so what's next? After agents that can plan.
Well, the next evolution takes us into what we call cognitive agents.
Cognitive.
Yep.
Sounds even more human-like.
That's the direction. These agents expand on the deliberative idea, but incorporate skills we usually associate with human intelligence.
Like what kind of skills?
Things like emotional and relational adaptability, advanced memory systems, sophisticated learning abilities. Think of them as AI trying to understand and interact more like we do.
Okay, now this is where it gets really compelling for everyday interactions. We're talking about something closer to truly collaborative, maybe even empathetic AI.
Potentially, yes. Research on conversational AI, for instance, has shown the immense value of integrating these more human-like skills.
How so?
Well, work by Chandra and colleagues in 2022 found that adding cognitive, relational, and emotional skills can significantly increase user trust, engagement, and satisfaction.
Which is huge in certain areas.
Absolutely critical in sectors like healthcare or customer service, where the user experience and the success of the operation are really tightly linked.
But there's a delicate balance here, isn't there? It sounds tricky.
It is.
We want them to be efficient at their tasks, do the job well, but also feel human-like. Can you actually have both? Or does one compromise the other?
That is the core challenge. Designing cognitive agents means finding that sweet spot between just getting the job done efficiently, what researchers call instrumental efficiency, and actually replicating those human-like qualities.
Push too hard on the human side, maybe it gets less efficient. Push too hard on efficiency, it feels cold and robotic.
Exactly. And trust plays a central role here. Cognitive agents, maybe more than any other type, must prioritize being explainable and transparent.
To build user trust.
Yes, and to align with societal values. This means we need robust learning frameworks, especially in high-risk areas like healthcare. We need ways to integrate symbolic reasoning, machine learning, and crucially, human-in-the-loop mechanisms.
Keeping humans involved to ensure fairness and accountability.
Precisely.
That's a lot to consider. Not just the mechanics, but the whole interaction, the ethics. Now, you mentioned learning. Is there a specific way these agents learn that enhances their adaptability?
Yes, and it's a powerful strategy that can enhance both reactive and the more advanced cognitive agents. We're talking about reinforcement learning, or RL.
RL. Heard a lot about that. How does it fit in here?
Well, a key takeaway is that RL allows agents to optimize their behavior through trial and error feedback, learning from the consequences of their actions.
Like learning by doing?
Exactly. It's particularly effective in tasks involving sequential decision-making where there's uncertainty, or what we call stochastic conditions.
Meaning things are a bit random or unpredictable.
Right. Outcomes aren't always the same, even if you do the same thing. Think about robotic navigation in a changing environment, or allocating resources when demand fluctuates.
So instead of being explicitly programmed for every single scenario, or even planning every single step like a deliberative agent.
They learn by trying things, seeing what happens, and adjusting.
It's like a smart kid learning to ride a bike.
Right.
Falling, getting back up, figuring out what works through experience.
That's a perfect analogy.
Yeah.
RL-equipped agents dynamically refine their strategies. They modify their exploratory behavior to adapt to rare or unexpected scenarios. And empirically, in experiments, they often outperform static designs that don't learn.
That ability to continuously learn and adapt in real time seems like a huge leap, especially for truly unpredictable environments.
It is. It's a major driver of progress in AI capabilities.
But, again, what are the challenges? It sounds powerful, maybe almost too good to be true sometimes.
Well, the computational requirements can be significant. Training RL agents takes a lot of data and processing.
Okay.
And there are challenges like slow convergence, meaning it takes a long time to learn effectively, and sensitivity to those random variations we talked about.
So small changes in the environment could throw off the learning.
They can, yeah. Which highlights the need for innovations like hyperparameter tuning.
Which is like
carefully adjusting the dials on the learning algorithm itself to make it learn more efficiently and reliably. But connecting this to the bigger picture, RL also introduces a risk of opacity.
Opacity, meaning we can't see inside a black box.
Essentially, yes. Agents can develop strategies that are highly effective, but really difficult for humans to interpret or understand why they work.
And that raises some serious questions, right? Especially in sensitive areas.
Definitely. In healthcare or finance, for example, you really want to know why the AI is recommending a certain treatment or investment strategy. How do we balance that incredible adaptability with the need for explainability?
It found a solution, but we can't follow its logic.
Right. So there's an ongoing, very active search for methods that ensure we build in ethical safeguards. Things like using safe, exploratory training environments where it can learn without real-world consequences, and having human supervision mechanisms.
Keeping that human-in-the-loop idea strong.
Absolutely essential for trust and safety.
Wow. Okay, so we've really climbed that ladder. From simple stimulus response
To reactive agents coping with dynamic worlds.
to deliberative agents that plan ahead.
And cognitive agents aiming for more human-like interaction and understanding.
With reinforcement learning acting as this powerful adaptability engine underneath,
Sure.
capable of boosting several of these types.
It's quite an evolutionary journey, showing this clear progression. Simple agents give you efficiency and predictability, but they lack adaptability. Reactive agents bring real-time responsiveness. Deliberative agents enable strategic planning and goal chasing. And cognitive agents add that layer of human-like intelligence and social adaptability, focusing on interaction and trust.
So, wrapping this up, what does this all mean for you, the listener, as AI continues its incredibly rapid development?
Well, it means these architectures we've discussed, simple, reactive, deliberative, cognitive challenge, they form the very basis, the building blocks, for designing artificial agents that can tackle incredibly diverse challenges, often in dynamic, high-impact situations.
So understanding these different types gives you a crucial lens, right?
Yeah.
To view and interact with the AI that's shaping our world.
Exactly. From a simple automated response you get online all the way to a complex conversational partner that seems to understand you, knowing the underlying architecture helps you understand its capabilities, its limitations, and maybe even how to interact with it more effectively.
Which leads to a final thought. As AI becomes more and more deeply integrated into our lives, into our work, our homes, how do we ensure its continued development prioritizes not just more advanced capabilities, not just raw power,
but also transparency, ethical accountability, and a true understanding of what it means to collaborate effectively with intelligence, both human and artificial?
Something to really think about.